We now talk about Galois correspondence. So say you have a Galois extension K over F, and if you have a Galois extension you also have a Galois group, so that is nothing but group of automorphisms of K which fix F. So the Galois correspondence says that the intermediate fields E, that the fields between K and F, they are in one-to-one correspondence with subgroups of group G, so subgroups of this Galois group of the extension. So this is how it is generally pictured. So you have field F and over it you have field K, and you have some intermediate field E. So corresponding to this there are groups. So obviously there is a group G which is the Galois group here which fixes field F. So this group fixes field F. We are saying this subgroup H is fixing field E, and obviously the identity map fixes K. So this identity map is nothing but this Galois group of K over K. This is our Galois group of K over F. So this is fixing F. So this H should fix E. So this is what we are saying. So this H should possibly fix E. So K over E. So we have to show that there is one-to-one correspondence. So obviously we have to construct a map from the fields to the Galois groups, and from this Galois groups back to the fields. So in this direction the map is like this. You take a field E and you attach to it a Galois group. So we are saying this H, if it corresponds to E, so if there is one-to-one correspondence, then this H is precisely that which will fix E. And correspondingly you take any subgroup here, say you have subgroup H here, you take it and you come back to field is precisely the elements which are fixed by this subgroup H. So obviously H is a subgroup of G, and therefore it is a subgroup of automorphisms of K. So now we have to show that these two maps are inverses to each other. So we have to show H to KH, so this map, and this E to the Galois groups of K over E, that is automorphisms of K which fix E. These are inverse to each other. So we are starting from H, you go to KH. Now you want to come back, we'll use precisely this formula above. So if you want to come back, so you will have Galois, this K is the topmost field, so K remains the same, and since we are using this result instead of E, we have K of H. Now this has to be equal to this and then we are done. But we have a result in from this lecture, Galois extensions and groups, that this Galois of K over KH is precisely H. So one direction is done. You go from H to KH. From KH you apply this formula back, you get H. Now we have to do the same for E. From E we go to this Galois K over E. So that is our group, and then when you go back here you have to use the topmost field K, and then here you have raised to the H, here you raise to Galois K over E, and if this is equal to this, then we are done. And our claim is that K over E is Galois. So if K over E is Galois, this would imply that Galois K of E is E. Again, this result, this part of the result, this was discussed again in this lecture. So Galois K over E, this K and K would cancel out, only thing you have is E. So again you will get this result. So E to this Galois group, which is group of automorphisms of K which fixes E, and from here if you go back you will just get E, that is K group of automorphisms of K which fix E is just E. So this is our claim. We have to prove this. If we prove this, the rest just follows from this lecture. These two results, this result and this result, are in this lecture. So to prove this, first notice that in the lecture on Galois if and only if normal and separable, we showed that K over F is Galois if and only if K is splitting field of a separable polynomial. So in fact we showed that K over F is Galois if and only if K is normal and separable, but we also proved this direction in this lecture, Galois if and only if normal and separable, and the other direction we had proven in the lecture automorphisms of splitting fields. So this is the result we are going to use. Anyway, you can find this result on page 552 of Dummett and Foote, second edition. So we want to use this result to prove this result. So we already know that K over F is Galois. So say therefore K is a splitting field for some polynomial f over f. That is, f of x lies in f. So this f lies within this field f and then adjoin x to it. So if K is a splitting field for f over f, it is also a splitting field for this f of x and e of x, because this e contains f. So the splitting field will remain the same for the polynomial even if you extend the field, where K contains e which contains f. So therefore K over f is Galois implies K over e is Galois, because you still have constructed this same splitting field of a separable polynomial. So if you have a separable polynomial f of x in this f of x, that is f over f, then you get K over e for free, because if f lies in f of x, then obviously f would lie in e of x and the splitting field would not change. So we have proven the claim that K over e is Galois, and therefore this result holds. So notice that this K contains e and e contains f, and here we have opposite direction. This 1 is contained in h is contained in g. So obviously we have talked about this before. 1 corresponds to Galois K over K, because the ID map is precisely the group of automorphisms of K which fix the entire K itself. So now we talk about inclusion reversion. So say h1 contains h2 if and only if kh1 is contained in kh, that is, fixed field of h1 is contained in fixed field of h2. So h1 contains h2, this implies this direction is clear. Obviously, you know, if h2 is a subgroup of h1, then h2 at the bare minimum will have to fix k of h1, because all the elements of h2 lie in h1. So this will hold, and this direction would also hold, because now kh1 is a smaller field than kh2, so there is more freedom on choosing permutations here, because you have to fix only a smaller field here, so there is more freedom here. Here you have to fix a larger field, so there is less freedom here. So this holds. So this implies this, but this is already equal to h1 and this is already equal to h2. Again we are using the similar kind of result here. So again this implies h1 contains h2. So h1 contains h2 implies kh1 lies in kh2, and which again implies this. So you have if and only if. So another important result is this. So say H is the subgroup, KH is the fixed field, and K over F is G. So this obviously is true, because K over F is a Galois extension and G is the Galois group. So this just follows from the definition here. And this is given to you. If this is given to you, now divide this by this. So if you divide this equation by this equation, you get K over F, and here this is order of G divided by order of H. H is a subgroup of G, so therefore you write it as G over H. Yeah. So this is order of G divided by order of H is precisely this. So obviously if you write it like this, this becomes KH over F, because this is K over F is precisely K over KH and then KH over F. So notice that these two cancel out to get K over F. But if you divide by K over KH, so then this portion will go away. What you're left with this is this. So what does this mean? So this means, say we have this K here, corresponding to H you have field here and you have F here. So you have this. So we are given that K over F is G. So K over F is G, which is the size of our Galois group. Then what is KH over F? So kh over f is nothing but order of G divided by order of H. So we write it like this, G over H. So G is the full group and this is the smaller portion. So we can generalize this. Instead of just talking about G and H, we can talk about two fields here, say H1 and H2. So say we are given a tower like this. This is F, then there is KH2, KH1 and K. So obviously corresponding to K, you just have identity. Corresponding to this, you have subgroup H1, you have subgroup H2, and here you just have Galois group G. So because this automorphisms which fix F, so these are all subgroups. So containment is in this direction. So K contains KH1, KH1 contains KH2, KH2 contains F. Here H1 contains identity, H2 contains H1, G contains H2. So the question is, what is this degree of extension? So what is KH1 over KH2? So what is this degree of extension KH1 KH2? So again you use the similar kind of method and the answer would be obvious. It is order of this group H2 divided by order of group H1, which we will write it like this. So this just dividing the order gives you the degree of extension.